Student carried out an experiment to determine the number of carbon-carbon double bonds in a molecule of cooking oil by measuring the volume of bromine water. Oh, they had this in a GCSE question once. Student followed these instructions. Use a drop and pipette to add 5 drops of oil to 5 centimeters cubed of inert organic solvent in a conical flask. Use a funnel to fill a burette with bromine water. Add bromine water from a burette to the solution in the conical flask and swirl the flask at each addition to measure the volume of bromine water that is decolorized. Student results are shown in Table 2. Table 2. In a trial experiment, the student failed to fill the burette correctly so that the gap between the tap still contained air. Okay, so what effect does this have on the measured volume of bromine in this trial? Okay, so the measured volume of bromine would be higher. And the reason for that is that if you imagine I'll try and badly draw a burette here. This is the sort of tap region there. This is our nozzle. Great word. Love the word nozzle. This is a bubble. Okay, it's in orange as well, look. This is our bromine water here. Now ideally we'd want this to be right down to the end, but it's not. This bubble here, and that is actually affecting the volume. So this, if we go right up to the top, and this is meniscus, this is measuring 41, dead on. Actually this may account for 0.4. So actually in reality the bromine there is 36.4. No, I don't know. Yeah, basically the volume of bromine there is less than we think, so it's going to make this air is going to make the reading. It's pushing this higher up than it would normally be. It would drop without this air here. It would drop down. In my case, 0.4 because I'm saying that's what, or 0.3, or whatever I said that is in here. So it's making the reading higher than it should have been. Explain your answer. Yeah, okay, so the explanation here is that it's pushing up, but actually 0.4 of this, okay, if we release this, if I'm sticking with 0.4, that 0.4 fills this space before it leaves. So we would fill this air pocket first, and then we start to distribute. But still, when we look at the value here, 41 will have gone down. Even if we filled this and nothing came out, 41 will have actually dropped down to 41.4. Although none have come out. But actually when we measured this, we would find that 41.4 was our new value, so we would measure 0.4 having been released. So it's a bit of a sort of a strange one. Very practical question, that one, but not too difficult of a question either. 7.2. Other than incorrect use of burettes, just reason for the inconsistency in the student's results. Right, well let's look back at what's happened. So he's using a dropping pipette to add 5 drops of oil. That's pathetic. You can't just use a pipette to add 5 drops of oil. A drop isn't a unit of measurement, so drop sizes could vary, and that obviously is fairly pathetic as far as an experiment goes. You're not going to get very good results there at all unless you can guarantee the size of each drop, which of course you can't. Outline how the student could improve this practical procedure to determine the number of carbon-carbon double bonds in the molecules of the oil so that more consistent results are obtained. So what could the student do? Okay, so essentially what you're trying to do really, as you hopefully the idea of drop sizes varying, we're trying to eradicate that. So rather than using just random here, let's add a volume. So choose volume of oil, dissolve in the solvent as was before. Then we're going to make it into a volumetric solution, so make standard solution using more solvent. Yeah, we'll do it in a volumetric flask. Or just a conical flask, either would work. And then titrate. We'll titrate against it using the bromine water. So what we're doing is we're cutting out that sort of the chaff. We're choosing a proper volume of oil there. We then are actually using proper numbers, and we can work stuff out basically using what we know is now a 250 centimetre cubed sample. We titrate, say, 25 centimetre cubed samples from that using the bromine water, and we're getting a real good data there that's super accurate, provided that we do everything obviously accurately. Super accurate results, as opposed to just do some random bits and all this. It's quite pathetic really, this 5 drops of oil. So that's really about the best thing you could do in that to actually improve what's going on. So, some calculations now. 7.4. The oil has a density of 0.92 grams centimeter cubed. Each of the 5 drops of oil has a volume of. So they are saying now actually the volume, the drops are of the same volume. Woo! Some good maths going on here. So, the oil has a density. Okay, so let's use some of these numbers that we've got here. So we know the density of our oil, and we know ultimately the volume of our oil. So we've got 5 drops. We need to times this by 5. So the volume. So straight away, let's work out a mass of oil. Because we can see obviously density ties together mass and volume. So mass of oil is going to be 0.92 times by 5 times 5 times 10 to the minus 2. So what I'm doing there is I'm accounting for the 5 drops and my density there. And I'm going to come up with a number there of 0.23 grams of oil. So I know I've got 0.23 grams of oil. I can work out also, I've got an MR there, I can work out my moles, this is of oil, I should say. My moles of oil, therefore, are going to be moles mass over MR, 0.23 divided by 885, and that's going to give me a number of 2.6 times 10 to the minus 4. Now what I can also do here is I've got bromine water, and I'm told to use experiment 1. Now, experiment 1 gives me the volume of bromine water used, so 39.4. Concentration is moles over volume, so moles is concentration times volume. So moles of bromine water is going to be concentration 2 times 10 to the minus 2 times 39.4. Obviously taking into account, we need to convert that, and that's going to give us a number of moles of bromine. So I know that this number of moles of oil required this number of moles of bromine ultimately. So all I'm looking for is a ratio of oil to bromine. So my ratio currently is 2.6 times 10 to the minus 4 to 7.9 times 10 to the minus 4. And when I look at that ratio wise, if I divide by the smallest number, which is this one, I come out with a ratio of 1 to 3. So I know, therefore, that for every 1 molecule, ultimately, of oil that I had, I required 3 molecules of bromine water, which therefore means I must have had 3 double bonds in there to require the 3 bromine molecules. So there we go. 3. Easy. It's not too bad, actually. It's a lot harder when I looked at it than actually it was in reality.